and peers. This is Dr. Jones checking in. Good to virtually see you back. Let's dig in. We were on A&P1, lecture test 1, video 19. We did the chart at the top of page 26. Oh, more water balloons. And we were about to dig into diffusion. So, terms you need to know. First is permeability. Permeability is the property of a membrane that determines what can cross the membrane. So this is about whether or not things can cross the membrane. So it might be, the membrane might be permeable to water, but impermeable to solutes. It might be permeable to solutes, but impermeable to water. So it can be permeable to different things. Impermeable means that nothing can cross. So there's like a brick wall. Nothing gets through a brick wall. Freely permeable means anything can cross. So this would be like an archway, but without a door. Just an open archway. Anything can fit through the archway. And selectively permeable is like a locked door. If you have the key, you can get in. If you do not have a key, you cannot get in. So it's selectively permeable. Some things can cross the membrane and some things can't. Okay. Passive processes are processes that do not require ATP to move stuff across the membrane, and active processes require ATP, which is a high energy compound. So when I say ATP, it sort of means energy, but specifically it means ATP. So it requires energy, specifically ATP, to move stuff across the membrane. Okay, next slide. No, not gonna. Okay, there's an arrow on the keyboard. I can use that. There we go. All right, terms to know. Diffusion. Diffusion is the movement of a substance from an area of high concentration to an area of low concentration. And I know I go through these kind of fast, and I do lecture kind of fast anyway, but in person y'all would tell me to repeat things, and I would repeat things, although not endlessly, usually once. But here in the videos you can always pause and go back, rewind, watch it again until you get the whole thing. So diffusion is movement of a substance from an area of high concentration to an area of low concentration. Concentration gradient is a difference between the area of high concentration and low concentration. And just so you know, when I have high concentration written down, I have it like this. This is the chemistry symbol for the word concentration. And I don't think I've spelled out the word concentration since I learned that in the last 20 years. So diffusion from an area of high concentration to an area of low concentration. And concentration gradient is the difference between the area of high concentration and the area of low concentration. So here's our picture of diffusion. You've got our purple sugar cube going into the water. So right here we have tons of purple sugar, and out here we have no purple sugar. So there's a very high concentration gradient because there's there's a few purple sugar waters, and here there's no purple sugars. So there's a very high concentration gradient because there's a very big difference between the concentration, the high concentration area, and the low concentration area, which doesn't have any yet. And then as it diffuses out, we talked about Brownian movement and the random molecular motion. And of course, heat will increase that random molecular motion. And here you're seeing it start, the purple sugar molecules start to diffuse out. And then at equilibrium, you'll have, in equilibrium, a balance. The purple sugar molecules are as likely to be anywhere in the sample as anywhere else. So equilibrium is an even mixture where there is no concentration gradient, an even mixture with no concentration gradient. So does diffusion tend to exaggerate or eliminate the concentration gradient? So diffusion goes this way to equilibrium. So we have eliminated the concentration gradient, and that's what diffusion does. It eliminates concentration gradients. If you want to maintain a concentration gradient, you have to maintain a barrier, like say a plasma lemma, also called a plasma membrane, also called a cell membrane. And that is in fact one of the main functions of our cell membranes, is to maintain concentration gradients. We talked about there was more potassium inside the cell and more sodium outside the cell than in, and more proteins in the cell than out of the cell. Those are all concentration gradients, which we're also going to call, I don't know, today, tomorrow, a chemical gradient. So concentration gradient and a chemical gradient are the same thing. So I wanted to give you a quick demonstration of diffusion because we can. So here's my mason jar, because I didn't grow up on a farm, but both of my parents did, and so it's a thing. Mason jars. And the fancy schmancy lid, because I love them. All right, and then I have my solute. Have we had the term solute yet? Nope. Okay, the solute is the stuff you put in the solution. Wait. No, that's not the right term. Yeah, aqueous solution is water. Do we not have those terms? All right. Solvent. All right. So the solute here, the solute in our example, I'm pointing to the screen where you can't see it. Mouse. The solute here is the purple sugar. Solute. And the solvent is the water. We talked about an aqueous solution. In an aqueous solution, the solvent is water. Solvent. And then our equilibrium here is our solution. And remember, if you're not part of the solution, you're part of the precipitate. Okay, so things that don't dissolve in water will precipitate out, like they will rain out, and then you'll get like a clump of it on the bottom, and that's the precipitate. So if you're not part of the solution, you're part of the precipitate. I warned you about the science jokes, right? We already had the science joke conversation. I could maybe help it, but what fun would that be? All right. So I have here Crystal Light with caffeine, and that's my solute is purple caffeine sugar water, and it's probably got sugar in it. And then my solvent is water, and then I'm going to, y'all see that? My hands are in the way. There you go. There you go. It diffuses a whole lot faster. The liquid diffuses a whole lot faster than the powders. We do still have a concentration gradient. We're not at equilibrium yet because there's still some clear-ish water at the top, although as I move it a little bit, trying to hold it still here, there you go, diffusion in action. And it would diffuse faster if it were warm. Another thing that'll make it diffuse faster is increased motion. So, shut the lid here. Shake it up. Not shake it off, shake it up. Make sure the lid is on or you will shake it off. All right, and so now we have a nice clear equilibrium of caffeine water. Yay, caffeine. All right, now I get to drink caffeine in just a second. All right, coffee's still better, but it's good. Okay, so in the example of the purple sugar cube dissolving in water, the solvent is water, aqueous solution, and the solutes are purple dye and sugar. And when it reaches equilibrium, there'll be a solution of purple sugar water, or Kool-Aid, or whatever it is. The concentration gradient is also called the chemical gradient. Oh, definitely today. I told you we'd get to that. Chemical gradient, which when combined with the electrical gradient, remember it was negative on the inside and positive on the outside, that is the electrical gradient. So when we combine the chemical gradient with the electrical gradient, we get the electrochemical gradient. I have to spell that, electro. Remember, we take two word roots, put an O in between them and smush, and we got a new word. Electrochemical gradient, which is already spelled for you. But I'm already writing, so there you go. The electrical gradient plus the chemical gradient, which is the concentration gradient, equals, and together they make the electrochemical gradient. Half circled and half squared. That's odd. Maybe it's a flag or a fish. It just needs a tail. And I told you I couldn't draw. There you go. It's clearly fishy. Now it's an angry fish. All right, I'll leave the art to my husband and my daughter. Okay, so what does it mean to move down the concentration gradient? That is to diffuse. Let's see what's on the next slide. Was I supposed to show you the next slide already? Oh yeah, I had these, yeah, there they are. I knew they were somewhere. Okay, what is an aqueous solution? It's where the solvent is water. Remember, water is H2O, which is our little Mickey Mouse. It's a covalent bond. So what does it mean to move down the concentration gradient? It means to diffuse. And you need to know these terms. I have said them and defined them before, but let's make sure we get them written down because you absolutely need to know these two terms for the next 2 semesters. It doesn't go away. So hydrophilic is water-loving. These are water-soluble things. Like anything that dissolves in water as a solvent is hydrophilic. So Crystal Light caffeine water is hydrophilic. Like cinnamon is not. Cinnamon will not dissolve in water. Cinnamon is hydrophobic. It is water-searing. It is fat-soluble. So I like cinnamon in my oatmeal. I like cranberries in my oatmeal. And the cinnamon, if you put the cinnamon just in the oatmeal, it floats on the top when you put the water in it. And then there's like plain flavorless oatmeal with like a layer of cinnamon on the top. And that's not okay. So I use the sweetened, the dried sweetened cranberries. And so I mix the cinnamon in with the cranberries, and then it sticks to the sugar on the cranberries, and then you get the cinnamon flavor all through the oatmeal. So there you go. I am not a chef by any means, so any tips or tricks I have, you're welcome to them for what that's worth. Oh, and the picture. Okay, so we've got purple. I'm showing you the little cylinders of purple. So concentration gradient and then a solution. Okay, I'm going to move it. All right, page 27. Moving on. Diffusion and plasma membranes. Okay, arrow. There we go. What diffuses across the cell membrane? What substances enter and leave the cell through simple diffusion? Alcohol, fatty acids, steroids, lipid-soluble drugs, and dissolved gases. The gases that we care about are oxygen molecules, not oxygen atoms, and carbon dioxide, CO2, which we also looked at and drew. All right. Channel-mediated diffusion allows water and specific ions through integral membrane channels. Again, if it's a true-false in the note set, it is always true. True-false in the tests, you gotta read those. These, true. Passive channels called leak channels are always open. And the leak channels are specific. So sodium leak channels only allow sodium through. Potassium leak channels only allow potassium through. Okay. Osmosis. It's next. Okay. All right. In the way. There we go. You have to swoop it just right. Terms to know. Osmosis is the diffusion of water across a selectively permeable membrane. Osmosis occurs across a selectively permeable membrane that is freely permeable to water, but not freely permeable to solutes. In osmosis, water flows across a selectively permeable membrane towards the solution that has a higher concentration of solutes, because that is where the concentration of water is lower. That means it moves down its concentration gradient. Osmotic pressure is the force of water diffusing across the membrane, and this is not measurable. So here you have lots of water molecules with a few solute molecules, and on this B side you have fewer water molecules and more solute molecules. So A here has a higher concentration of water, B has a lower concentration of water, and water moves across the selectively permeable membrane to the area with the higher solute concentration, which is saying it backwards because everything moves down its concentration gradient. And here there's a high concentration of water, and here there's a low concentration of water. And so water is moving down its concentration gradient. Now, of course, the solute concentration is the opposite. So it is moving towards the higher solute concentration, but that's not why. It's doing it because it's moving down its own concentration gradient, because that's what diffusion is. Like, you can't stop it unless you've got like a not the right kind of membrane there. Okay, so the force of the water moving through the holes in the selectively permeable membrane is osmotic pressure. So it's the force of water moving due to osmosis. Now that is not measurable, but we can apply an opposite force, undo the osmosis till the volumes are equal. And we can put a spring on this and measure the force applied, and that is hydrostatic pressure. So hydrostatic pressure is a pressure required to undo or to oppose osmotic pressure, and it's a pressure that we can measure. So that's the number we use. It's a measurable force that opposes osmotic pressure. Okay. Osmolarity is the same as the osmotic concentration. It's the total solute concentration in an aqueous solution. So I put 1 squeeze of Crystal Light caffeine water in here. So it has 1 squeeze worth of osmotic concentration. If I put a second squeeze in here, I would double the osmolarity, because it would have twice as much solute in the same amount of liquid. And tonicity, and osmolarity is something you can measure, so this is a numbers thing. And tonicity describes the effect of the osmolarity on the cells. So the tonicity, there are 3 parts of tonicity. So let's talk about those. They're on the next slide. Oh, there's the arrow. They're on the next slide. First, we have isotonic. Iso means same. So this is the same osmolarity as the solution outside the cell is the same osmolarity as inside the cell. So it's isotonic, and the tonic means the tone. And so water will move out of the cell and water will move into the cell, but at the same rates, because the water is diffusing into the cell and out of the cell at the same rates. So we have no net movement. We have movement, but it's the same in and out. I'm going to put MVMT for movement because I'm like that. Okay, next we have hypotonic, and hypo means less. So if you put a cell in pure water, hypotonic, with a lower osmolarity than the inside of the cell, then the osmosis will bring water into the cell, but no water will move out of the cell. And this causes hemolysis. Hemo means blood, and lysis, as we know, means a loosening of. And here you see the cell, red blood cell, loses its biconcave disc shape and becomes like a balloon, like a water balloon. Literally, a water balloon. And then it can explode if it continues to take on water. So hemolysis is when the red blood cells explode. So isotonic is 1, hypotonic, which causes hemolysis, is 2. I promised you there were 3. Here we have hypertonic. Hyper means more, hypo means less. These are word roots that will not go away. Iso means same. You need these for the next 2 semesters. Hypertonic solution has a higher osmotic concentration than the inside of the cell. So osmosis, the water moves towards the higher osmotic concentration, from higher concentrations of water to lower concentrations of water, because that's what osmosis and diffusion are. And so, well, diffusion isn't necessarily water, although it can be. Osmosis is a form of diffusion. Anyway, hypertonic, the cell loses water and dries out, and that is called crenation, where it deflates and it gets spiky. So crenation is when the red blood cells shrink from losing water in a hypertonic solution. So we will start the chart on the next page in the next video. And that leaves 3 pages left. We'll probably do the last 3 pages all in one fell swoop, which we sometimes do. And I did not have a timer on. All right. Well, thank you as always for tuning in. The education must go on. This has been A&P 1, Lecture Test 1, Video 19, where we talked about diffusion and started osmosis. We will continue osmosis in the next video. Dr. J out.